Okay, welcome to lab here. And like I mentioned before, we're going to continue on and kind of finish up the last part of chapter 3 here, talking about nomenclature. And that will be good because scheduled for today is, I think, study assignment C, which is on nomenclature. So hopefully by the time we're done here, you should be able to name everything you ever wanted to name. Maybe stuff you don't want to name. I'm not sure. All right. So far, we've talked about a few different types of compounds that we named. They're basically all ionic compounds. We've had type 1 ionic compounds, which is between a metal and a nonmetal, where we have a transfer of electrons from the metal to the nonmetal, creating our cation and anion. Again, always when you have the metal and nonmetal that comes together, it's always really the metal that's the most important. And if the metal is a type 1 metal, which means again, it isn't from group 1, 2, or 3, or it's zinc, cadmium, or silver. That basically means they have fixed charges. So as we talked about and we did, we essentially just used the whole name of the metal, and the non-metal gets the IDE at the end of it. Again, just those two names together, regardless if there's two non-metals, three non-metals, four non-metals in the formula, no prefixes or anything like that. So just whole name of the metal, IDE on our non-metal. If we have a metal and non-metal and the metal is a transition metal, or something like tin, lead, antimony, bismuth, and that sort of area of the periodic table, they have variable charges, and we really name it the same way. We use the whole name of the metal, IDE for our non-metal. And the only difference is because they do have a variable charge, we do want to tell people what the charge is in the name, and that's what the Roman numeral is for. So we use a Roman numeral to indicate the positive charge that's there on the metal. And that then brought us to polyatomic ions, which are basically groups of nonmetals that are covalently bonded together through sharing of electrons, but do have charges. We do need to know the names of those guys. You do need to know the names and the formulas and the charges that all go together so that you could kind of put them together correctly. As we just finished talking at the end there, for the most part, you will usually find a polyatomic ion together with a metal, and that is because there's pretty much mostly negative. And what that really means is they really do follow sort of type 1 and type 2 sort of naming. So if the metal, again, does not need a Roman numeral, then you just use the whole name of the metal and the whole name of the polyatomic ion. If the metal does need a Roman numeral, we use the whole name of the metal and the Roman numeral and the whole name of the polyatomic ion. So those are the ionic type namings that we talked about. Any questions on any of that stuff that we talked about before there? Okay. So where we kind of left off here was with acids. So let's talk about acids and sort of how to name acids. And an acid is really something that produces an H plus ion in solution. It's able to produce free H plus in solution. When you talk about acids, H plus is sometimes referred to as a proton, and that is because hydrogen has a proton and an electron and no neutrons. So when it becomes positively charged, it's left with just a proton. So very common sort of acid-base chemistry, we have a proton. And pretty much all acids, the cation for all acids is H plus. So that's pretty much the cation always for a acid. The difference is the anion and whether or not the anion has oxygen. So when we go about sort of naming acids, the major thing that you want to look at is whether or not the acid has oxygen in the formula. And if it doesn't have oxygen, we will name it one way. If it does have oxygen, we would obviously name it a different way. So let's talk about that. Let's start with if the acid has no oxygen. If your acid has no oxygen, the way that we name the acid is we start with hydro, something, ic, acid. The kind of missing part is the anion part. So the missing part is the anion. So if we have something like HCl, no oxygen, so this would be hydrochloric acid. If we had, say, HBr, again, no oxygen involved, so this would be hydrobromic acid. So the key part here, if we have no oxygen involved in the acid, we always start with hydro, ends with ic, and the middle part is really the anion part of the name, goes in the middle there. You may also notice that I put this little symbol next to everybody, which is the aqueous symbol. So AQ means aqueous. Basically means a water environment. And that's really what makes that an acid, is being aqueous. That's really what an acid is. An acid is, as you'll learn in 200B, probably a little bit more, it's basically the ability in a solution to produce all these H pluses that are just kind of freely floating around by themselves, not really attached to anything. And that's why it is typical that you include the aqueous next to the actual formula for an acid. And that is because if we had something like this, for example, if we had HCl in the gas phase, this would not be hydrochloric acid. This would be known as hydrogen chloride. So the difference really between that guy and the bottom guy is that the aqueous symbol indicates that it is in solution, and thus the H plus has been liberated and freed, and it is an acid at that point. That, by the way, is how you make hydrochloric acid. You take a little hydrogen chloride gas and you kind of bubble it in water. And before you know it, you get some hydrochloric acid, basically. So when we do have something, by the way, that's just hydrogen and not an acid, like that, H plus and Cl minus, we just call it hydrogen to begin with. And hydrogen chloride, and if we had something like HBr, this would be hydrogen bromide. But here again, with the AQ next to it, it indicates that it's an acid, and we would call it hydrobromic acid. So important when you write the formula for acids that you usually do include the aqueous symbol next to it. Again, it indicates that we are dealing with an acid and not something that's a gas or something like that. So no oxygen in your acid, starts with hydro, ends with ic, and acid, again, make sure you include the aqueous symbol with it. So let's talk about what happens when we do have oxygen. So if the answer is yes, there is oxygen in my acid. The good or bad news is it will contain, at that point, a polyatomic ion, all those favorite things we just talked about. And if you remember, for the most part, our polyatomic ions end in one of two ways. It either ends in ate or ite. So if your acid does have oxygen and your polyatomic ion ends in ate, so your polyatomic ion ends in ate, the name of the acid is something ic acid. You ate too much, you feel icky. That's a good way to remember that, I suppose. So if you take something like HNO3 with the aqueous symbol, again, the NO3 here is nitrate. So this becomes nitric acid. The H2SO4. SO4 is sulfate. This becomes sulfuric acid. Now you may be wondering, why do we have two H's there? Again, as I mentioned before, in each of these cases, the cation is H+, which means in the case of nitrate, the anion is NO3-. So we just need one of each of those to get us to our acid formula. Now, when we have our cation, that is our H+, and our anion in the second case, which is our sulfate, when we put these together to balance out the charge, because it ultimately is an ionic compound, we actually need two hydrogens to balance that out. And that's how we get to H2SO4. And it's also known as a diprotic acid. It has two H's that could come off basically at one at a time. So if your polyatomic ion ends in 8, your acid will be something ic acid. That leaves us the other option, which would be if your acid ends in yes to oxygen and it ends in ite, your polyatomic ion, your acid name would be something OUS acid. So HNO2. NO2 is nitrite. This will become nitrous acid. H2SO3. SO3 is SO3 2-, which is sulfite. This will become sulfurous acid. So same deal here. Again, cation going to be our H+. Anion in the first case, NO2-. Again, +1, -1, only need one of each, which is how we get to this formula. And obviously in the second case, H+ is our cation, and our anion is SO3 2-. And much like the previous one, we need two hydrogens there to balance it out. So that's how we get to that formula. At no time did I mix any of these things together, which is a very common thing people like to do. They want to put hydro on every acid because it sounds cooler that way, I think. I'm just going to call it hydro, whatever acid. So hydro, again, only for ones with no oxygen. If it does have oxygen, you should not have hydro on it. And again, either will end in ic for the one with the most oxygen, or us, OUS, for the one with the least number of oxygen. And again, you should kind of put the aqueous symbol next to it. So why don't you try some here? Let's see if we had, let's go with H2S. Let's go with HI. Let's do H3PO4. Let's do H2CO3. All right, give a name of those acids there. Okay, so let's take a look here. So starting at the first one here, I see the aqueous symbol, probably a good idea. I see H as well, probably going to be an acid. I don't see oxygen, so I do know it should start with the hydro. So this should be hydro. Again, the middle part is the anion. Hydrosulfuric acid would be a winner, I think. Again, looking at the second one here, HI, also no oxygen involved. So we're going to go with the hydro as well. So this is going to be hydroiodic acid. Any question on those first two? No. No oxygen involved. Again, both starts with the hydro, both end with the ic, and obviously both have the acid part. All right. Rolling over here to the right-hand side, H3PO4. So obviously it does have oxygen. It is an acid, so we want to look at the polyatomic ion part. PO4 is PO43 minus. That is phosphate. Again, my polyatomic ion ends in 8, which means my acid should end in ic. So this would be phosphoric acid. Again, no hydro here because it has oxygen. So very common. People want to put that hydro in front, but it does not need it and should not have it. So phosphoric acid here. And lastly, on the bottom here, also an acid, also has oxygen. So isolating our polyatomic ion, that is CO3 or CO3 minus. That is our good friend carbonate. Again, ending in ATE, which means my acid should end in ic. So this becomes carbonic acid. Any questions on how to name acids? So again, it does involve whether or not there's oxygen or not, and that's kind of the main thing. And again, if there is oxygen, you're going to have that polyatomic ion present. Any questions on acids? All right, then let's talk about naming. I thought that's what we've been doing. All right, let's continue on. Type 3 compounds, which are 2 nonmetals. So these are a little bit different. These are molecular compounds. So these are guys that are sharing electrons. So remember that when we do get 2 nonmetals together, it does involve that sharing of electrons. No electrostatic attraction, no positive, negative, no cations. I will say that these guys are pretty much the easiest ones to really name, but they are also the ones that people screw up the most on because they want to do all kinds of weird things that they shouldn't do, and they always mess up on it. But these are actually the pretty simplest ones to kind of go about and name. These are the ones that I know everybody's been waiting for. These are actually the ones where we do use prefixes. So these are actually the place where you should use prefixes when you name these guys. And those are prefixes, as we will see, I think, in a table. But, you know, mono, which is 1, di, which is 2, tri, which is 3, tetra, which is 4, penta, which is 5, hexa, which is 6, hepta, which is 7, octa, which is 8, perhaps nona, which could be 10, 9. Deca would be 10, I suppose. Deca would go with 10. So these are the prefixes, and basically, when we go to name these type 3 guys, you pretty much use the appropriate prefix and the whole name of the first element in the formula. And then you use the prefix and the nonmetal name of the second guy with the IDE at the end. So whole name of the first guy with the appropriate prefix, IDE on the second one in the formula with the appropriate prefix. There are some rules when you kind of go about this, and the major rule is with mono a lot here. We do not use mono on the first name. But it is okay on the second. So you can use it on the second, you just can't use it on the first name. And as we will also see as well, since I think I'm jumping the gun anyways, but we'll just talk about it. Sometimes when you use the prefix and the first letter of the element, you'll sometimes get perhaps two O's to back up to each other, or like an A and an O. And usually we get rid of that prefix letter there, that last vowel on the prefix. So for example, if I had one oxygen, I would not call it monoxide, right? It is called monoxide. Again, we drop one of the O's there. And so when we have something like CO, this would be carbon monoxide. Again, carbon, nonmetal, oxygen, a nonmetal. One of each of them. Prefix is mono for both of them. Again, don't use mono on that first name, but can use it on the second name. And again, we drop that O typically. The only one that's usually okay in most cases, oddly, is a couple of I's that come back to each other. Seems to be okay. So that's okay if you kind of have that deal. But an O and an O, got to get rid of one of the O's. You got an A and an O, usually get rid of the A off of the prefix part of the name. Now, there is, that's pretty much what this says here. There is certain guys that, although they are nonmetals and nonmetals, they really do go by sort of the common name. And those are things, as we will see, things like H2O, which is water. You know, we do go by sort of those common names, but we'll talk about those in just a second here. So here's the official prefix list, much prettier looking than mine. But again, same idea there. We will drop the A off of the prefix. When we have an A and an O that comes together, again, two O's that come together, we drop the O. I and I, it's okay, it seems to be. And that's what we see here. Again, we see that with tetraoxide. Again, dropping that A off of the prefix, going to get us to just the O. And again, our two O's here, dropping the first O. As I mentioned before, there are certain things that have common names, and you should go by the common names. So H2O is water. It is not a trick question. If you see H2O, you should write water. It really is. Nobody wants a refreshing glass of dihydrogen monoxide. It doesn't sound that refreshing. Probably why they don't use that name when they're using it for bottled water. Have a nice glass of dihydrogen monoxide. Sounds good. So if you see H2O, obviously it's water. NH3 is ammonia. So this should not be confused with that polyatomic ion. This is NH3, no charge. And it's ammonia, which is a weak base. NH4 plus is the polyatomic ion. That's ammonium. So those two get confused super a lot, they say in the business there. So again, our polyatomic ion that we saw earlier is the ammonium ion. Ammonia is NH3. Two different things, oftentimes used together. Not such a good way. CH4 is another very common one that you sometimes come across. That is methane. That is your simplest organic molecule you could have. It's stuff that comes out when you light a Bunsen burner, the gas and all that good stuff. So those are some common ones, common names that should always kind of go by their common names. Water, ammonia, methane should definitely kind of go by those sort of common names. I think I also, again, talked about it a second ago, but just to reiterate, technically speaking, when we do deal with something like this, which is not an acid, like a gas, when we have this H plus and Cl minus, it's almost treated more like an ionic compound, even though they're both nonmetals coming together. So we don't use prefixes here for anybody. Again, it's just like we talked about, this would be hydrogen chloride because it's not the acid form. And if you had, say, something like H2S, this would be still hydrogen sulfide. Again, if this was a gas, which is hydrogen sulfide gas. So again, we don't typically use prefixes with hydrogen It's named more like an ionic compound where we just use hydrogen, even if there's more than one sort of hydrogen involved there. And again, if it's not an acid, as we just talked about, obviously if these were acids, this would be hydrochloric acid, hydrosulfuric acid, but in sort of the non-aqueous or acid version, we have H plus as the cation. It's just hydrogen and IDE for the second guy when we put them together. Any questions on that there? Okay. So why don't you try a few of these here and give the proper names. I'll give you some names. You can give some formulas as well. Go with dinitrogen pentoxide. Let's go with carbon tetrachloride. Let's go with dioxygen trisulfide. I'll just make it up. Why not? There we go. That. All right. So names for the guys on the left and formulas for the ones on the right. Okay, so let's take a look at these. Again, really, these should take you like 2 seconds because the nice thing about this when you see two nonmetals together is you don't have to worry about charges, you don't have to worry about anything other than basically picking the proper prefix and writing the names. So when I see I2O7, prefix for 2 is di, right? Prefix for 7 is hepta. And we pretty much just need to put it together. So again, we'll use the prefix and the whole name of the first one, which would be diiodine. Here, the two I's are okay. The second one here, we'll get the prefix. We are going to drop the A because the first letter of our second guy is oxygen, and oxygen gets the IDE treatment. So this is diiodine heptoxide. Again, prefix, exactly what we got going there. Second guy, name like normal, gets the IDE. First guy gets the whole name with the appropriate prefix. Any questions on that particular one? Coming down here, again, we see carbon and oxygen. They are both nonmetals. So we have one carbon, so prefix for one is mono. Prefix for two of our oxygens there is di. We do not use mono on the first name, so we would start with just carbon. And here we have di, and oxygen again gets the IDE at the end of it, so carbon dioxide. Coming down here, we have phosphorus, which is a nonmetal, Cl, which is a nonmetal. Again, we have one of the phosphorus, which is mono. We have three of the chlorines, which is tri. Same deal here. We're not going to use mono on the first name, but are going to use the entire first name of the metal here with, I hope we spelled that right, phosphorus. And we are going to go with tri for our second one. And chlorine, like normal, second one gets the IDE at the end of it. So phosphorus trichloride. Any questions on the names here? All right, I think almost just as easy, or probably easier than any of them, is when you have the name and want to write the formula here. So as soon as you read this name of dinitrogen pentoxide and you see those prefixes, you should be super happy because you just write what it says. Nitrogen is N, di is 2, oxygen is O, and penta is 5, and you are done with the formula right there. So N2O5, again, nothing to balance, nothing, to sort of Roman numerals, nothing crazy like that. Same thing here, carbon, I don't see a prefix, but I do see a prefix on the second one. Carbon and chlorine are both nonmetals. So again, no prefix on the first name means that there's just one, so we write C. Tetra is the prefix for 4, and chloride is Cl, so CCl4 would be our formula. And lastly here, dioxygen trisulfide. Again, the two prefixes tell me I just need to write what's there. So O and 2 for di, and S for sulfur, and 3 for tri. And we get some made up thing that probably doesn't exist, O2S3. Question on type 3. So again, people always want to use prefixes everywhere. This is actually the only place that you should use prefixes, is in a type 3 compound when you have two nonmetals together. As we also see here, no Roman numerals and prefixes. None of that stuff happens together. If you find yourself given a name with Roman numerals and prefixes, you probably should put the X on it yourself before I get to it. Yes, because it will be wrong. So make sure that you don't mix any of those things together. Roman numerals only for metals and nonmetals, where the metal is a transition metal. Prefixes only for non-metal, and no prefixes. All our Roman numerals needed for type 1 compounds. Any questions on any of those things? By the way, as you can see in all these names are the formulas. We don't use Roman numerals in formulas. That's also a very common thing people do, especially with type 2, is they write the formula, throw some Roman numerals in between the symbols. So none of that crazy stuff. Any questions on type 3 compounds? So let's see here. One last thing, just to kind of review a naming that we talked about, I think it was experiment 6. And since we're talking about names, let's talk about hydrates and names. And a reminder that hydrates are really two parts. There's the salt part and there's the water part. And remember, hydrates are these guys that have that little dot that comes between the salt part, which is an ionic compound, and the water part back here, right? So when we name these, we also use prefixes. And when we name these guys, the water is called hydrate. And we use a prefix to indicate how many waters there are. So for example, if I had MgSO4 dot 4H2O, we would name this the ionic part just like normal. So this is a type 1 compound, and this would be magnesium sulfate. And then when we get to the water part of the hydrate, 4 is tetra, so this would be tetrahydrate. So again, that's sort of how we go about naming hydrates. Water is always hydrate with the appropriate prefix. The salt part is always named like a normal type 1 or type 2, which means if you had something like CuNO32.6H2O, this here, if we just took the salt part first, copper is a type 2, which means we need to figure out the charge. We have nitrate, and there's 2 of them, which means we have a -2, and the copper here would have to be +2. So this would be copper Roman numeral 2, nitrate, just like we normally would name this. And again, we have 6 waters. This would be hexahydrate. So again, just to kind of review hydrate naming, since we're talking about officially naming, that's sort of the method there. And obviously, if you had a name, you could turn it into a formula. So if you had calcium sulfate heptahydrate, you would just take the ionic part there, which is calcium sulfate, which would be CaSO4 +2 -2. You would put the dot, hepta is 7, hydrate is water, and you would end up with this formula here. Any questions on hydrates? Any questions on naming? I think we've named everything you ever wanted to name or didn't want to name, I suppose. Again, until you get to maybe next semester, then you'll learn a few other things about complex ions. But up to there should be good. Question on any type of naming. So we talked about how to name all ionic guys, covalent guys, polyatomic ions. Any questions? Okay, so a couple of reminders again, quiz on Thursday on all the bonding stuff. We will lecture probably, maybe we'll stop lecture early and take the quiz either at the end of lecture or maybe at the beginning of the lab. I'll let you know on Thursday, but we'll take it like we've been taking everything else using Canvas, Proctorial, and then we'll talk about the lab, obviously, whatever's scheduled. I think it might even be another study assignment, so it might not be too much going on Thursday in terms of that. Since I took up some time here lecturing on this, I'm going to make the study assignment for today due on Thursday. So you can have the extra time if you like. If you want to turn it in before that, the assignment will be up there sort of for you to turn it in.